Welcome back, everyone. In part 2 of this lecture series, we're going to work on dealing with those newly created categorical variables. Let's go ahead and get started. Okay, here we are at the notebook where we left off last time. We now have a good mix of continuous variables as well as categorical ones. And some of these category ones that we created are string codes, which you may encounter in your real data sets. So we have both things that could be categorical or continuous, and we're going to now deal with them. So what we want to do first is separate them out from each other. So we'll create two variables, one called cat calls, or COLS, and those will be our categorical columns as strings. And that is going to be our, and then, next one we'll say AM or PM, and then finally we'll also say weekday. Something to keep in mind is that certain actual features can be treated as either continuous or categorical. And that's where it really depends on your domain experience if you should treat something as a category or as a continuous variable. As you can imagine, something like hour can be treated as there's 24 categories where every hour is a specific category, or a continuous variable that goes from 0 or 1 to 24. Again, it's up to you and what domain you're actually working in to decide whether you should treat something that is numerical but could be either continuous or categorical. We'll go ahead and just, for the sake of this exercise, keep it as categorical. That way you can learn how to deal with categories that present themselves either as integers or as strings. So we have those categorical columns, and let's go ahead and get our continuous columns. And for this, I'm going to save a little bit of typing time by grabbing all the columns by saying df.columns, and we'll go ahead and grab the pickup latitude. We'll say pickup longitude, latitude, drop off longitude, and drop off latitude, the passenger count, and then the distance in kilometers. And you can always copy and paste from our provided notebook. Okay, so here are my continuous columns that we'll use as features in our categorical columns. Next we're going to do is under yCall, we actually need to say what is the label we're going to use. And for this series of lectures, we're treating this as a regression problem, so our label is this fair amount. We'll use this fair class when we go through this same problem as a classification problem. Okay, so there is our fair amount, and now what we're going to do is we'll go ahead and use pandas in order to deal with these categories. So pandas offers a category data type for converting categorical values to numerical codes. There's lots of different ways you can encode these categorical features into numerics so that your neural network can actually understand this. But let me show you a little bit of work you can do with pandas, and then we'll kind of do this to the rest of our categorical columns. So first, I want to convert our three categorical columns to actually have a category data type. So if we say df dtypes right now, notice that right now these categorical columns, such as hour and AM or PM, if we scroll down, right now AM or PM, those are our objects, and hour is integer 64. I'm going to use pandas to actually change this data type into a category. So the way I can do that is I can say for category or for cat in cat calls, go ahead and say df of cat is now equal to df of cat. However, I'm going to change as type and say category. So go ahead and run that, and then go ahead and say df dtypes, run that again, and you'll notice now these three have a special data type called category. So let's go ahead and explore df hour, just ahead of that kind of series, and you'll see here that pandas has now recognized this as a category, and it says, hey, there's 24 different categories, 0, 1, 2, 3, and so on. Let's check it out for AM or PM. Check out the head of that series, and you'll notice it also recognizes there's two categories now, either AM or PM. And then finally, we'll do the same for that weekday column. Go ahead and get the head of that here. And now it's also smart enough to understand that there's 7 category objects: Friday, Monday, Saturday, Sunday, Thursday, Tuesday, and Wednesday. Okay, so the days of the week. Now what we're going to go ahead and do is explore that there's actually category codes and then categories. I want to quickly explore these categorical and code attributes so we can understand what we're using them for later on. Let's go ahead and just grab, for instance, AM or PM. So I can say df AM or PM. So that's our series, and if you kind of scroll all the way down past 120,000 of them, again, it reports back we have categories, objects, AM, PM. So let's imagine that I actually just wanted to grab the information on the categories, just AM or PM. What I could do is come back up here and say .cat .categories. Run that, and it reports back just those categories. And those categories also have codes. So I could say .cat .codes, and essentially each one of those string categories, AM or PM, actually has a numerical code. So we can see here that AM is 0 and then PM is 1. So you only see zeros and ones here. Let's kind of continue this example by showing it to you on the weekday. So you can see that as well. So there's the weekday. Let's go ahead and explore the categories again. So categories, run that. We have Friday, Monday, Saturday, Sunday. But if I were to ask for the codes themselves, I can see here I've essentially taken these strings and encoded them numerically, 1, 2, 3, 0, 4. That's actually extremely similar to the same way we already had, if we scroll back up here, the hour column structured. So you can see here the hour. And as I mentioned before, it's kind of up to you and your domain knowledge to treat hour as continuous or as categorical. Both methods could be correct. So we'll come back down here, and now we understand that now that we have these as data type category, there's .cat codes, which are those numerical values, and .cat categories, which are those actual kind of string codes. And what I can do here is say .cat .codes, and if I call .values off of this, then this reports it back as a NumPy array. And recall that when we're turning things into tensors, we first need them in a NumPy array format, and then we can cast them into a PyTorch tensor. So what we're going to do here is create these large NumPy arrays using this .cat .codes .values. So we'll say, let's go ahead and make 3 variables. We'll say HR is equal to df hour .cat .codes .values. We'll do the same thing for AM PM. Set that equal to AM or PM .cat .codes .values. And then finally we'll also say weekday is equal to df, and we'll say weekday .cat .codes .values. Okay, so if we look at right now any of these arrays, they're kind of just these large flat arrays. What I want to do is kind of stack them together. So what I will do then is do the following. I'll say that my categories is equal to np.stack, and then as a list I'm going to pass in HR, AM, PM, and weekday. And what this is going to do, it's going to stack them together so they're in the same format as they originally were in the actual data frame. And the last thing I want to do is I have to specify what axis I kind of want to stack this along. And since I want them as columns, I'll stack them along axis equal to 1. So go ahead and run that, and then when you look at cats, you get something that looks like this. So I have 4, 0, 1. And this essentially indicates that the hour was 4, AM or PM had the code 0, which was AM, and then weekday was 1, which was whatever the first weekday was in our category. So that was a Friday. And so this np stack, basically these two commands of converting everything to values and then stacking them together along axis equal to 1, we're able to convert what we had here in our original data frame as string codes and a mix of categorical columns, so that AM, that hour, we're able to then convert it into a NumPy array, where we actually specifically know that each of these numbers is going to represent a specific category. Okay. Now you may be wondering, why not just use pandas .mapping ability or some sort of apply function to convert pandas and use some code that's not the category to actually convert it into these numbers yourself? Well, the reason for that is technically everything we just did, because we're using pandas category data type, you could do this all as a list comprehension. And the reason that's really nice is because then this suddenly scales to whatever data frame or data you're working with. And you can copy and paste the command for that from the notebook, but essentially this is everything we just did as kind of a one-liner, where we use a list comprehension here to grab every column in the categorical columns and grab those values and then stack them together. So what's really nice about this is essentially all you need to do for your data set is define this cat calls. So if we come back up here, recall that we defined cat calls again here. What we did is we just chose kind of, hey, which features are we going to treat as categorical? So you would open up your own data set and kind of make a list here. I'll treat, hour, AM, or PM, or weekday as features. Then once you have your little list here, you'll scroll down, do something like this, convert them all to category, and then your third line would just be this right here. The rest of this code here was kind of just to show you what was going on. But now you are able to do this exact same process on your own data with just 3 lines of code. And again, we really want to show you that you can use this notebook and this lecture as a blueprint for your own regression problems. And then in the next series of lectures, we'll show you how to use this as a classification problem. But the actual process for all of this will be the same in either regression or classification. So I hope you kind of see how nice of a tool this is. All right, so I'll go ahead and comment that out since we kind of already ran it ourselves. Next, what we're going to do is convert this NumPy array into a tensor. So what we can do here is say cats is equal to torch.tensor and pass in cats, and then we'll just say the D type is now just torch integer 64-bit. Since we now know, since these are all categories, they'll always just be integers. You won't get any floating point numbers there. And now finally, let's go ahead and repeat this same process of converting everything to a PyTorch tensor for our continuous variables. Now for the continuous one, it's going to be a lot simpler, and in fact we can use this sort of list comprehension notation along with np stack. So what I'll do here is I'll say, in fact, I'm going to say df call dot values instead of cat codes values. It's just dot values because I'm going to be doing this for the columns in my continuous columns. And then we'll do the same thing here. Just pass this guy into np stack along axis is equal to 1. And then we'll set that to a variable called conts. So this is a line you can essentially always run regardless of your data set here, because you'll just have to set up your own continuous columns list. So if you take a look at our lecture notebook, and if you've really understood what we've done here so far, you should be able to see how you can map this to essentially any data set you want. We'll go ahead and run this. There we go. And if you get some sort of error, make sure you didn't commit any typos by checking out our lecture notebooks. So right now, this const, this is essentially just a NumPy array. Let's go ahead and transform it to a tensor. We'll say continuous values, torch tensor, pass in those continuous values, but in this case, the data type should be torch.float because we're going to keep that sort of precision. Go ahead and run that, and now if you take a look at continuous, it's going to be a tensor. Okay, so now we have both the categorical variables and the continuous variables as PyTorch tensors. There's one last column we need to take care of, and of course that is the label. Let's go ahead and convert the label into a tensor. So we'll do that by grabbing that y column. So remember, we actually defined it as y call. So if you run that, that is technically just calling the fair amount column. And what we want is just the values as a NumPy array. And we'll go ahead and convert that to a torch.tensor. And then say d type is equal to torch.float. And something else you should notice here is take a look at the braces. I have 2 sets of braces here in my shape, but when you run torch.tensor, depending on what version of PyTorch you have, sometimes it doesn't keep this shape. If you're using our environment, you shouldn't have an issue and it should stay like this, but just in case it doesn't, and you get some errors along the way, maybe you're using a slightly older version of PyTorch, you can always reshape -1 to 1 to confirm that it's going to keep this column shape instead of one long flat array. So that's why we have that reshape -1, 1 in the actual lecture notebook. But if you're using our environment, it should not be necessary. So just keep that in mind. And then we'll say y is equal to this. And let's take a look at everything we have. We have our categorical tensor, which is 120,000 points with 3 different categories, or 3 categorical columns, I should say. we have the continuous shape, which is 120,000 records with 6 continuous features. And then finally we have Y shape, which is same records, 1 Y label per row. Now the last thing we need to do is set up our embedding size for the categorical columns. If you actually take a look at the next lecture, we'll be defining a tabular model, which is going to be able to take in the categorical columns and their embeddings. And so the embeddings that we're going to be using is an embedding layer that comes with PyTorch. If we actually check out the documentation page for this layer, which is torch.nn.embedding, and we'll be using that in the very next lecture, essentially what this does is create a simple lookup table that stores embeddings of a fixed dictionary and size. And essentially all this really means it's just the one-hot encoding that actually occurs to the categories. Now it's often used to also store word embeddings and retrieve them using indices. You can imagine that if you're working with text data that has words, each word is then going to have a kind of index assigned to it. So A would be 1, and then the would be 2. Another word would be 3 and 4 and so on. So we're actually not using text data, but we are using different categories. So the same idea applies. We essentially just want to one-hot encode them, and that's what this simple lookup table does. You can think of this as just kind of one-hot encoding. And if you want more details on what PyTorch embedding does, the technical details are here in the documentation. You can explore these, but for simplicity, just think of it as one-hot encoding those categories. And there's also a great Quora link here. If you check out the lecture, or if you just Google search, what does PyTorch embedding do on Quora, there's a really nice answer here given. And again, it's kind of just explaining that it's doing the one-hot encoding, such as 100. And you often really see it in examples of working with text data because by definition, you have to categorize those words. Okay, so let's come back here and show you how we can set our embedding sizes. So we'll go ahead and first grab our category sizes. So our category sizes, we'll do this with a little bit of list comprehension to save some space. We'll check the length of dfcall.cat.categories. And we'll say for call in our category columns. So what does that actually mean? Well, if you check out cat sizes, this basically just reports back how many separate or unique categories we had. So we had 24 hours in a day, 2 was AM, PM, 7, that's how many days in the week we have. And again, you can always expand this to now your own code, since it's just dependent on what you decide cat calls is going to be. Next, we want to set our embedding sizes based off these categories. So the way we do that is the general rule of thumb is that you just divide the number of unique entries in each column by 2, but you should max out at around 50. So the way we do this is we just say EMB, SZS, or whatever you want to call it, and we'll say go ahead and take size, and then min between 50, or size plus 1 floor division with 2 for size in cat sizes. Okay, so what is this actually doing? Essentially, for size in cat sizes, so for the numbers 24, 2, and 7, it's going to look at it and it's going to either take 50 or divide it by 2, depending on what the actual value is. So if we take a look at the results here, for our embedding sizes, since none of these exceeded 50, we essentially have the halves, 12, 1, and 4. Okay, and the reason we say plus 1 and these 2 forward slashes is we don't want these to be floats, so that's what these 2 forward slashes are for, and then plus 1 is just in case you only have 2 categories. All right, so that's it for this lecture, and what we're going to do next is go ahead and define a tabular model and set up our network. We'll see you there.